Okay, so this problem says let K be a field of characteristic 0 such that every odd degree polynomial f in with coefficients in K has a root in K. Let L over K be a finite extension. Show that the degree of L over K is a power of 2. So we need to show that the degree of the extension L over K is a power of 2. And so notice that this is in some sense a generalization of what we know to be true for R and C, right? R is a field such that every odd degree polynomial has a root in R, has a real root by the intermediate value theorem. C is a finite extension of R, and in fact, its degree is 2, which is a power of 2. Okay, so we have some kind of generalization of that idea here. Um, so um, let's prove this. So first of all, since L is a finite extension of a field of characteristic 0, or more generally, any perfect field, L over K is a separable extension. All right, a finite extension of a perfect field is going to be separable. So since K is characteristic 0, it's perfect, and L is a finite extension, so L over K, this is a separable extension. Um, which means that the minimal polynomial of any uh, element of L, um, minimal polynomial for any element of L over K is going to be a separable polynomial. Um, Now, since L over K is a finite separable extension, there exists an extension M of K containing L such that the extension M over K is going to be Galois. So uh, this is namely the Galois closure, which Galois closure M over K of the finite separable extension L over K, which always exists and is minimal in the sense that um, in any fixed algebraic closure of M, uh, any other Galois extension of K containing L will contain M. Um, and also we should note that M over K is a finite extension as well. And this is because if you look at how the Galois closure is constructed, it's some subfield of the composite of the splitting fields of the minimal polynomials for this finite basis of L as a vector space over K. So in particular, this extension M over K will be a finite extension as well. Um, okay, and that means, so what's our picture here? So we have the tower of field extensions, M over L over K. Now, if we can show that the degree of M over K is a power of 2, then it will follow by multiplicity of degree that the degree of L over K is also a power of 2, right? If you're a power of 2, you only have 2's in your prime factorization, so if this degree is a power of 2, then this degree has to be as well. All right. So let's try to show that the degree of M over K is a power of 2. So since M over K is a Galois extension, we can consider the Galois group. So consider the Galois group, which is the automorphisms of M that fix K. We'll call this group G. Um, so note that we can write the order of the automorphism, right? So automorphisms of M fixing K, which will always be less than or equal to the degree of M over K, since the degree of M over K is finite. This is finite. And so the order of this group, um, right, this is a group under composition. But the order of this group will be, we can say 2 to the n times M for some M that's odd. Um, okay, that's just uh, getting rid of the 2's in the prime factorization of the order of the group. So note that G has a CeLO 2 subgroup H of order 2 to the n. Now, it's true that n could be 0, in which case this CeLO 2 subgroup would just be the identity. If that's the case, though, it will turn out that L over K was just the trivial extension anyways. And so it still works. It's still a power of 2. It's just 2 to the degree of L over K would be 1, which is 2 to the 0. Um, okay. So now we know that CeLO 2, CeLO P subgroups exist. So this a subgroup H has order 2 to the n, and its index in G is M, our odd number. So now we get to apply the fundamental theorem of Galois theory. So um, by the fundamental theorem of Galois theory, so we have this correspondence between subgroups for a Galois extension like M over K. We have this correspondence between subgroups of the automorphisms of M fixing K and subfields of M containing K. Um, and in particular, so G is some subgroup of the, I mean, H is some subgroup of the automorphism group, and so it corresponds to some fixed field. So the fixed field of H, let's call it E, um, which, just to be sure, is the subfield of M that is fixed by the elements, which are automorphisms in H. Right, so remember, H is a subgroup of G. G is the set of all automorphisms of M fixing K. So if H is a subset of those, then they're all going to fix K, but they might fix more than just K. So, so the uh, E is going to um, be somewhere there, possibly um, a priori at least, possibly in between M and K. It's a subfield of M, and it's the subfield of M that's fixed by all the elements in the subgroup H of the automorphisms of M fixing K, which is our G. Um, so what does the fundamental theorem of Galois theory says? It also says that the um, degree of the fixed field over the base field. So to complete the sentence, the degree of E over K is equal to the index of H in the G, which are automorphisms of M fixing K, the group of automorphisms of M fixing K. And we know that the index of H and G is M because, remember, H is the CeLO 2 subgroup, so M is its index, which is odd. Okay, so now let's think about this extension E over K. Well, since E over K is a finite extension of a field of characteristic 0, E over K is separable. It's a separable extension. And since E over K is a finite separable extension, the primitive element theorem says that any finite um, separable extension is a simple extension. So by the primitive element theorem, E is equal to K adjoin alpha for some alpha in E. So, okay, alpha is, an element of some finite extension of K. So in particular, it's algebraic over K, and therefore it has some minimal polynomial. And let's think about the minimal polynomial of alpha over k. So now the minimum polynomial of alpha over k has degree, um, well, the degree of the minimal polynomial of alpha over k is equal to the degree of the extension k of alpha over k, which is, we just said e over k, which is m, which is odd. Um, and so therefore the minimal polynomial of alpha over k, so it has coefficients in k, so what was the hypothesis of the problem? It was that uh, every odd degree polynomial with coefficients in k has a root in k. So m alpha k of x uh, has a root in k by the assumption of the problem. But what is the minimal polynomial? Well, the minimal polynomial is the unique monic irreducible um, polynomial such that alpha is a root of it with coefficients in k, such that alpha is a root of it, and in particular, it's irreducible, right? But the minimum polynomial is irreducible, and over a field, um, if you having a root is equivalent to having a linear factor, right? So if you had a root, then you'd have a linear factor. So for it to be irreducible, it must actually be linear. So the minimal polynomial hence must be linear. So if it's linear, then its degree is 1. So m is equal to 1. So what we find out then is that the size of the automorphism group of m over k is equal to 2 to the n. And finally, since m over k is Galois, the size of the automorphism group of m over k is equal to the degree of m over k. It's always less than or equal to, but since it's Galois, it's actually equal. And so the degree of m over k is also 2 to the n. And that's what we wanted to show, right? The degree, now by multiplicity of degree, this implies that the degree of L over K is a power of 2. And that completes the proof for this problem.